All right, so we saw that the actual demonstration equipment was a little bit frustrating to use because it doesn't exactly match up to the theory. But we do have a simulation I could show you. And let me do that really quick. And just to remind you of the problem I'm talking about, I'll put this back up on the board really quick. We had this crazy problem where we had two sources and we had a wavelength of 1.2 meters approximately. We've got a separation of the sources of about 2 meters, and there's some points 3 meters, and we wanted to learn about all this stuff. So now let's go to a screen share. And so what I've done here, hopefully this will look a little bit better, is I'm trying to look at this. 1, 2, 3 wavelengths is 360. So notice here, lambda is 1.2 meters approximately. Right here we see separation is 200 centimeters. That means this is 2 meters. A lot of times this symbol is given the letter D in homework problems. So let's say D equals 2 meters. What else do we have here? Right now I only have one source on, so there's no interference pattern. Was there another thing? Oh, and the frequency. We're assuming V is about 343 meters per second. That's the speed of sound, so sometimes we use the letter C for that. And from that, we found a frequency that I think was about, what was it, 283, something like that. I still have it written up there. Let me check. 283, yeah. All right, so in this case, let me erase some of this, but not all of it. Let's get rid of this crap. All right, and this. All right, and so now I should be able to turn on both speakers and run this. Now it's going to take a second for the pattern to develop. And while that's developing, I think the distance we wanted was something like 3 meters, right? That's pretty close. That's not quite good enough. And we had, I think it was 3 meters from the top source right here. So I'm looking at, let me get my annotations. Come on, oh, I don't want the eraser, I want the draw. And okay, what color can I get here? There we go. Right here was, oops, put another one right out here. Those were the 2 points we were talking about. This was point A, I think, and this was point B. Just confirming. Yes, that's true. And so notice here at point A, we said if you set the frequency at 283, we should get a dead spot or a sound minimum. And notice what's happening at point A. It's getting kind of messy there. But you could see that the color is light gray instead of white and black alternating. Why is it light gray? I got to just clear these. Let's get this circle out of here. It's blocking the view. But so in this case, we see the white from the top speaker is canceling the black from the bottom speaker, and we get essentially light gray, meaning no overpressure there, which is the same as not hearing sound. All right, and then if we, let me get rid of this. So what if we go to the midline right here? Notice at point B, we get maximum oscillation between black and white, so that would be a loud spot. All right. And then for fun, we said, what will happen if you sweep the frequency, but stay on point A? So if we stay on point A and we change the frequency, let's bump it up a little bit. Give it a minute to respond. Notice the pattern changes. A higher frequency is a shorter wavelength, and we see more detail in the pattern. Notice if we keep going up, eventually, point A should become an interference maximum, and we're getting there. Let's crank it all the way. Give it a minute to respond. And so now we can see point A is quite close to a constructive interference. So as you sweep the frequency up or down, that's going to change the interference pattern. Notice higher frequencies, shorter wavelengths, tighter pattern. What if we try the separation? Make a prediction what will happen when I sweep the separation. So I'm going to increase the separation. Will there be more of these? And maybe to help you understand that question, let's talk a little bit. Let's clear all my annotations. And then let's go back. Let me do this. We kind of see this line here. We see a line here. That's the midline. We see a line here. And notice it's kind of a hyperbola, but I'm just going to do the straight line portions of it. So we see those red lines on the screen are indicating interference maxima. All right. And now my question is, what happens if I change the separation? So if I increase the separation, do you think that pattern of red lines, the interference maxima pattern, do you think that will increase? Or do you think it will get tighter together? Will we see more of those red lines on the screen? Or do you think the pattern will expand? Will we see less of them? If you want to pause the video and think for a minute, go ahead. I'm going to change the separation in 1, 2, 3. Here we go. All right, so we cranked up the separation. Let's see what happens to the number of interference maxima and minima. That might not be what you were expecting. We see more as you spread it out. So if the sources are more spread out, we see more interference maxima and minima, and that means it would be harder to get the microphone placed at one of those spots. So conversely, if we shrink the separation, the pattern actually expands. And now notice we've got, oh, that's kind of interesting. The second red line sort of lines up on a minima, and the top red line ends up on a maxima again. So we see that a number of factors affect the interference pattern. Separation, more detailed pattern. More frequency, more detailed pattern. All right, so more frequency means shorter wavelength. I think that's good enough. Let's stop that.